Hi, today we are going to talk about the charge distribution of polarized dielectrics. We have said before in a previous lecture that in dielectrics we have no free charges. So when some dielectric undergoes an influence of external electric fields, the positive charges cannot abandon to one side and the negative charges cannot abandon to the other side. And this is because the positive and negative charges are bounded through molecules inside the dielectric. There is no free charges inside the dielectric. So instead, the charges will be polarized, and in each molecule we will have a partially negatively charged side and partially positively charged side, and also they will be aligned in this way. As we see, under the influence of the electric field, we will have a bunch of dipoles inside the dielectric, and we will have a dipole moment vector which is directing to this side, okay? So as we said, this alignment of these all dipoles inside the dielectric will construct a huge polarization. And now we are going to find a smooth point function which is expressing this situation of the polarization. Okay, now let's start by the summation of the dipole moment due to each dipole inside the dielectric. Okay, we are going to take the summation, the vector summation for each dipole. Okay, and this is the vector sum of the induced dipole moments contained inside the dielectric. Now, if we want to find for example, the polarization due to some point inside this dielectric, okay, we are going firstly to divide it by the elemental volume. Now we have the dipole moment per unit volume. If we want to find the generalized volume density of the electric dipole moment, we are going to make this volume so small. What I mean by this, let's assume that this volume is containing these two dipoles right there, okay? I want to find the electric dipole due to some point. I want to find the electric dipole density due to some point inside this volume, okay? I want to make this volume tends to 0. And by this, we will have the volume density of the electric dipole moment, and this is denoted by P vector, okay? And to distinguish between this volume density of the dipole moment and the dipole moment, I choose the uppercase P to represent the volume density of the electric dipole moment. And as you notice, this whole statement that I said more and more, the volume density of the electric dipole moment is so long statement. So instead of it, we are going to use the term polarization. Now let's assume that we have some point in the free space, okay? Let's say that this point P, and we wish to find the potential due to the potential at this point due to this polarized dielectric. We know that this potential at P is produced by the punch of these aligned dipoles, and we know that each dipole has a potential, and this potential is found by, and this potential is equal to this equation is used to find the potential due to some dipole where this lowercase p is the dipole moment and r is the distance between the center of the dipole and the point. And due to the derivation of this formula, we have derived it in a previous video that I'm going to leave the link in the description. As we have a continuous dipole moment inside this polarized dielectric, we are going to find initially the dipole moment due to this elemental value. Okay, let's call this elemental value by dv. Okay, and to avoid the ambiguity between the coordinates for the dielectric and the point, I'm going to specialize the primed coordinates for the dielectric and the unprimed coordinates for the point. Now the dipole moment is due to this differential area. This differential volume is equal to dP is equal to the volume density of the electric dipole moment inside this area, or the polarization, okay, times the volume of this area, which is dV primed. Now substitute this, the right hand side of this term, for P in this equation, and we will have, okay, and this is the potential due to this differential volume. To find the potential due to this whole dielectric, we are going to take the integration for this whole volume, okay? So I'm going to put right there V primed to denote that this integration for the whole volume. Before diving into the integration operation, I'm going to take all constants outside. Now to make this formula more readable, I'm going to apply a small trick. Now let's look. Let's talk about R. R is representing the distance between this point, okay, P, and this point, which exists inside the dielectric, okay. This is R. Actually, this point has the coordinates of x, y, z. Remember that we said that the unprimed coordinates are taken for the point, and this point has the coordinates of x primed, y primed, and z primed. And as this R is distance, its magnitude can be found by the rule of the distance between 2 points, which is, and this is the square distance between P and this point. Now the trick that we are going to apply is right there. We are going to take the gradient, okay, of the reciprocal of R. We are going to take the gradient with respect to the coordinates of the dielectric, okay. Now we all know what is the gradient. The gradient is the spatial derivatives with respect to the 3 coordinate system for this scalar value, or namely it is, and as this gradient is primed, I'm not going to forget the prime for this variables. Okay, now let's firstly take the derivative for the reciprocal of R with respect to x. The value of this reciprocal of R can be found by this. I'm going to substitute the right hand side of this for R in this. We all know how to do this derivative. I prefer to start differentiation by the innermost term and then going outside. So I'm going to start by taking the derivative for minus x primed, which is minus 1. The derivative of x minus x primed with respect to x primed is, now the derivative of this whole term is minus half, as this whole thing is equal to R, okay. This whole thing is equal to R, so this is equal to this square root of R. So the final answer is going to be R to the power of minus 3. Now by applying 101 algebra, this is equal to, and regarding to the derivatives with respect to y and z, the answer is going to be homogeneous with this term, but instead of x, just put y. Just do this by yourself, and you will reach to the same answer that I'm going to write down there. Okay, now we are going to apply a simplification over this. We are going to do another trick. Just notice that x, we said that x is the location of P with respect to x-axis, okay, and x primed is the location of this point inside the dielectric with respect to x coordinate. So x minus x primed is the displacement in the let's say the horizontal axis, okay? X minus x primed is vectors, okay? And this vector is equal to ax, which is the unit vector, times x minus x primed. And the same thing for y minus y primed, which is the horizontal, which is the vertical displacement, from this point to this point. And the same thing for z minus z primed is the axial displacement from this point to this point. Now substitute the right hand sides of these three terms for the homogeneous for the similar terms inside this equation, and we will have. And notice that this summation is equal to the radial vector. Okay, this summation is equal to the radial location of the radial displacement between this point and this point. So this will be ended with this all summation is equal to the vector r, which is representing the displacement from this point to this point, as this vector is equal to the unit vector a sub r times the distance, which is r. By doing some algebra, this is going to be simplified into. Now notice that we can substitute this unit vector a sub r divided by r by the gradient of the reciprocal of r. So this is going to be turned into, from this formula we receive this new form of the formula, which is this. Now we have a vector identity that we can exploit. I'm going to write this vector identity down there. Okay, now look at this formula. I'm going to rewrite this now I'm going to rewrite this, okay, and make this term, this left hand side term on one side, and we will have. Okay, and notice that this formula is linking between the divergence and the gradient operators, and f is the scalar value, and a is a vector quantity. And now let's apply this over this formula, and in this case p is equal to a and f is equal to 1 over r. Okay, now apply this to this, into this, and we will have. And now let's apply the divergence theorem. The divergence theorem is telling us that the volume integral for the divergence of some vector value is equal to the surface integral for this, vector value. Okay. Okay, and as you see, this surface that we are going to integrate around is closed and vector as well. Let's say that this surface, the magnitude of this surface, or the magnitude of this vector, is equal to the area of this surface, which is ds. Okay, and the direction of this vector is normal to this surface. Okay, a sub n, which is the unit vector, which is the normal unit vector. So ds, the vector ds is equal to ds, which is the area, times an, which is the unit vector. Okay, now so that therefore I'm going to rewrite this in this form. Now I'm going to apply the divergence theorem that I expressed over this left term, and we are going to have. Okay, now what is the meaning of this? To understand what is the meaning of this, just consider some arbitrary volume. Okay, consider some arbitrary volume like this. For example, to find the potential at some point P, okay, due to this continuous distribution this continuous distribution of charge through this whole volume, we can't use this form of the potential formula because we don't have a discrete distribution of charges. So we are going to take a differential volume from this arbitrary volume like this, okay, and we are going to call it by, let's say, dV, okay, and by assuming that this charge, that this volume has a homogeneous distribution of charges, so we have a charge density, and we can calculate the potential by using this formula. And we are using this to find the potential due to a distribution of charges over a volume, to find the potential due to distribution of charges over surface. Okay, we are going to use the surface charge density instead of the volume charge density, and we will have. Now I want you to compare between equation 1 and the right hand side of this equation, which this one, okay, and equation 2 and the left hand side of the right hand side, I mean, okay, of this side. You can see that the dot product between the polarization and the normal vector is equal to the surface charge density, is equal to this. Yeah, just look, it's equal to it. And I used for the polarization surface charge density these double subscripts P and S. P corresponds to the polarization, which constituted the charge density, and S corresponds to the surface charge density. And note that the volume charge density in this case is equal to the divergence of the polarization. And I used just a single subscript P, which corresponds to the polarization, as the subscript S is distinguishing between this volume and the surface charge densities. And so the potential in this equation can be rewritten in terms of these two polarization charge densities as follows. This is the new form of the potential. Now let's interpret this equation. This equation asserts that the polarization of the dielectric material leads to the generation of both volume and surface polarization charge densities, which collectively contribute to the potential produced by this polarized dielectric. And regarding to the charge density, rho sub Ps corresponds to the surface charge density of the single charges that lie on the surface. What I mean by this rho sub Ps corresponds to only single charges that exist on the surface, and rho sub P corresponds to the volume density of the remaining charges inside the dielectric media away from the surface. And it's worth mentioning that in this video we found these charge densities mathematically. They could be found also physically, but I will explain I will explain this in another video to avoid prolonging. So I will stop here and terminate this video. So see you in the next lecture.